Studies Section 7. Differential and difference equations. Differential equations. These are equations that express explicitly or implicitly the relationship between a function y equal to f of t and one or more of its derivatives or differentials. The following are examples of differential equations. dy dt is equal to dt plus 9, equation 7.1. Y prime is equal to 12y. Y prime prime minus 2y prime plus 19 is equal to 0. These equations above are called ordinary differential equations because they have single independent variable. The integral of a differential equation is any equation without derivative or differential, that is, defined over an interval and satisfies the differential equation for all the values of the independent variables in the interval. Example 1. To evaluate this differential equation, y prime prime function of t is equal to 7 for all function y function of t that satisfy the equation, we simply integrate both sides of the equation to find the integrals. Y prime of t is equal to integral 7 dt is equal to 70 plus c1, equation 7.2. Y function of t is equal to integral 70 plus c1 in brackets dt is equal to 3.5 t squared plus c1t plus c. This is known as the general solution that shows when c is unspecified, a differential equation has an infinite number of possible solutions. However, if c is specified, the differential equation has a particular or definite solution which alone of all possible solutions is relevant. The differential equation order is the order of the highest derivative in the equation, and degree of a differential equation is the highest power to which the derivative of highest order is raised. Example 2. A. dy dt is equal to 2s plus 6, first order, first degree. B. dy dt in bracket raised to power 4 minus 5 dt is equal to 0, first order, fourth degree. C. d square y dt squared plus dy dt in bracket raised to power 3 plus x squared is equal to 0, second order, first degree. D. d squared y over dt squared in bracket raised to power 7 plus d cube y over dt cube in bracket raised to power 5 is equal to 75y, third order, fifth degree. First order linear differential equation formula. The situation whereby the derivative dy dt appears only in the first degree, and so does the dependent variable y, and whereby no product of the form y dy dt occurs. When the equation is called linear, the first order linear differential equation will generally take the form dy dt plus vy is equal to z, equation 7.3, where v and z may be constants or functions of time. The formula for a general solution is y function of t is equal to L raised to power minus integral v dt, bracket open, a plus integral z L raised to power integral v dt, bracket closed, equation 7.4. Where a is an arbitrary constant, there are two parts to the solution. L raised to power integral v dt, integral z L raised to power v dt is called the particular integral. This particular integral yp equals the intertemporal equilibrium level of v function of t The complementary function yc represents the deviation from the equilibrium. For v function of t to be dynamically stable, yc must approach 0 as t approaches infinity. That is, k in e raised to power kt must be negative. Solution of any differential equation can be checked by differentiation. Example: the differential equation general solution of this function dy dt plus 4y is equal to 12 is given as follows. Since v is equal to 4 and z is equal to 12, substitute in equation 7.4. Y function of t is equal to L raised to power minus integral 4 dt, bracket open, a plus integral 12 L raised to power integral 4 dt, bracket closed, equation 7.5. From the integration rules, integral 4 dt is equal to 4t plus c. In equation 7.5, c is ignored and subsumed under a. Thus, y function of t is equal to L raised to power minus 4t, bracket open, a plus integral 12 L raised to power 4t dt, bracket closed, equation 7.6. Integrating the remaining integral gives integral 12 L raised to power 4t dt is equal to 3L raised to power 4t plus c. Ignoring c again and substitute in equation 7.6, y function of t is equal to L raised to power minus 4t, bracket open, a plus 3L raised to power 4t, bracket closed, is equal to AL raised to power minus 4t plus 3, equation 7.7. Since L raised to power minus 4t, L raised to power 4t is equal to L raised to power 0 is equal to 1. As t approaches infinity, yc is equal to AL raised to power minus 4t approaches 0, and y function of t approaches y is equal to 3. The intertemporal equilibrium level, yt is dynamically stable. All these illustrations above are what are known as the non-homogeneous case of differential equations. The homogeneous case: given the function dy dt plus ut bracket y is equal to w into bracket t, equation 7.8. If u and w are constant functions and if w happens to be identically 0, then equation 7.8 will become dy dt plus ay is equal to 0, equation 7.9. Where a is constant, this differential equation is homogeneous on the account of the zero constant term. The defining features of a homogeneous equation is that when all the variables here, dy dt and y, are multiplied by a given constant, the equation remains valid. This feature holds if the constant term is 0, but will be lost if the constant term is not 0. An alternative to equation 2.2 is given as 1 over y dy dt is equal to minus a, equation 7.10. The solution to equation 7.9 or 7.10 is y function of t is equal to al raised to power minus at, general solution, equation 7.11, or y function of t is equal to y into bracket 0 L raised to power minus at, definite solution, equation 7.12. General solution occurs as a result of the arbitrary constant a, but when any particular value is substituted for a, the solution becomes a particular solution of equation 7.9. There is an infinite number of particular solutions, one for each possible value of a, including the value y of 0, which is the only value that can make the solution satisfy the initial condition. Equation 7.12 will be referred to as the definite solution of the differential equation 7.9 or 7.10, since it represents the result of definitizing the arbitrary constants. Exercise 1. Find the general solution of dy dt plus 3t squared y is equal to t squared, where v is equal to 3t squared and z is equal to t squared. 2. Calculate the definite solution when y of 0 is equal to 1 in question 1. Second order differential equations. These equations require separate solutions for the complementary function yc and the particular integral yp. The general solution is the sum of the two y function of t is equal to yc plus yp, given the second order linear differential equation. Y prime prime function of t plus bi yi function of t plus b2y function of t is equal to a, question 7.13, where b1, b2, and a are constants. The particular integral will be yp is equal to a over b2. b2 is not equal to 0, question 7.14. yp is equal to a t over b1. b2 is equal to 0. b1 is not equal to 0. Equation 7.15. yp is equal to a t squared over 2. b1 is equal to b2 is equal to 0. Equation 7.16. The complementary function is where yc is equal to y1 plus y2. Equation 7.17. y1 is equal to a1 L raised to power RT, equation 7.18. y2 is equal to a2 L raised to power R2 T, equation 7.19. And R2 is equal to minus B1 plus or minus square root of B1 squared minus 4B2 over 2, equation 7.20. Here, A1 and A2 are arbitrary constants, and B1 squared is not equal to 4B2. R1 and R2 are referred to as characteristic roots, and equation 7.20 is the solution to the characteristic or auxiliary equation R squared plus B1R plus B2 is equal to 0. Example 1. Find the particular integral for each of the following equations. 1. Y prime prime function of t minus 5y prime function of t plus 4y function of t is equal to 2. Using equation 30, we have yp is equal to 2 over 4 is equal to 1 over 2. Equation 7.21. 2. Y prime prime the function of t plus 3y prime function of t is equal to 12. Using equation 31, yp is equal to 12t over 3 is equal to 4t. Equation 7.22. 3. Y prime prime t in bracket is equal to 16. Using equation 32, yp is equal to 16t squared over 2 is equal to 8t squared. Equation 7.23. Example 2. The complementary functions for equation 1 and 2 in example 1 above are calculated as: for equation 1, R1, R2 is equal to plus 5 plus or minus square root of minus 5 in bracket squared minus 4 into bracket 4 over 2 is equal to 5 plus or minus 3 over 2 is equal to 1 or 4. Substituting in equations 3.1 and 3.2, and finally in 3.0, yc is equal to a1 L raised to power t plus a2L raised to power 4t, equation 7.24. For equation 2, R1, R2 is equal to minus 3 plus or minus square root of bracket 3 squared minus 4 bracket 0 over 2 is equal to minus 3 plus or minus 3 over 2 is equal to 0 minus 3. Thus, yc is equal to a1 L raised to power 0 plus a2 L raised to power minus 3t is equal to a1 plus a2 L raised to power minus 3t, equation 7.26. For equation 3, R1, R2 is equal to 0 plus minus square root of 0 minus 4 into bracket 0 over 2 is equal to 0, equation 7.27. YC is equal to A1 L raised to power 0 plus A2 L raised to power 0 is equal to A1 plus A2. Example 3. The general solution of a differential equation is composed of the complementary function and the particular integral. That is, y function of t is equal to yc plus yp. From example 1, the general solutions to equation 1 and 2 are: for equation 1, y function of t is equal to a1 L raised to power 1 plus a2 L raised to power 4t plus 1 over 2, equation 7.28. For equation 2, y function of t is equal to a1 plus a2 L raised to power minus 3t plus 4t, equation 7.29. Example 4. The definite solution for equation 4.0 is calculated as: let's assume y function of 0 is equal to 5 raised to power 5.5 and y prime of 0 is equal to 11. Then, thus y prime, the function of t, is equal to a1 L raised to power t plus 4a2 L raised to power 4t, equation 7.31. Evaluating equation 4.2 and 4.3 at t is equal to 0 and setting y function of 0 is equal to 5.5 and y prime function of 0 is equal to 1 from the initial conditions. Y function of 0 is equal to a1L raised to power 0 plus a2L raised to power 4 into bracket 0 plus 1 over 2 is equal to 5 whole number 1 over 2, equation 7.32 is equal to a1 plus a2 is equal to 5. Y prime function of 0 is equal to a1 L raised to power 0 plus 4a2 L raised to power 4 into bracket 0 is equal to 11. Equation 7.33 is equal to a1 plus 4a2 is equal to 11. Solving equation 4.4 and 4.5 simultaneously, a1 is 3 and a2 is equal to 2. Substituting in equation 4.0, y function of t is equal to 3L raised to power t plus 2L raised to power 4t plus 1 over 2, equation 7.34. Difference equations. The difference equations are equations that show the relationship between a dependent variable and lagged independent variables, which changes at discrete interval of time. For example, Ct is equal to f into bracket yt minus 1 t, bracket closed, where I, y, and t are measured at the end of each year. The difference equation order is determined by the greatest number of periods lag. The difference equation first order shows a time lag of 1 period, a second order 2 periods. The change in y as t changes from t to tt is called the first difference of y, which is written as dy over dt is equal to dyt. It's equal to yt plus 1 minus y, equation 7.35. The pattern of change is now represented by the difference quotient dy over dt, which is the discrete time counterpart of the derivative dy dt. The solution of a difference equation defines y for every value of t and does not contain a difference expression. Example 1. It plus 1 is equal to alpha into bracket yt minus 1. Order 1. Qst minus 1 is equal to a plus bpt minus 2. Order 2. Yt plus 3 minus 9yt plus 2 plus 2yt plus 1 plus 6yt is equal to 8. Order 3. dyt is equal to 5yt. Order 1. Example 2. If the initial value of y is y0, the difference equation yt plus 1 is equal to byt. Equation 7.36. Solution by successively substituting t is equal to 0, 1, 2, 3, etc. will be t is equal to 0, y1 is equal to by0, t is equal to 1, y2 is equal to by1 is equal to b into bracket by0 is equal to b squared y0. T is equal to 2, y3 is equal to by2 plus b into bracket b squared y0 is equal to b cubed y0. T is equal to 3, y4 is equal to by3 minus b into bracket b cubed y0 is equal to b raised to power 4 y0. Therefore, for any period, yt is equal to b raised to power t y0. This method is called the iterative method. Since y0 is a constant, notice the crucial role b plays in determining values for y as t changes. First order linear difference equations general formula. A linear first order difference equation is an equation where all the variables are raised to the first power without any cross product. For the example, yt is equal to byt minus 1 plus a, equation 7.37. Where b and a are constants, the general formula for a definite solution is yt is equal to bracket open y0 minus a over 1 minus b bracket closed b raised to power t plus a over 1 minus b when b is not equal to 1, equation 7.38. yt is equal to y0 plus at where b is equal to 1, equation 7.39. In a case where no initial condition is given, an arbitrary constant a is used for y0 minus a over 1 minus b bracket in equation 7.38 and for y0 in equation 7.39. This is called the general solution. Example, solve this difference equation. Yt is equal to minus 7yt minus 1 plus 16 and y0 is equal to 5 in the equation. B is equal to minus 7 and a is equal to 16. B is not equal to 1. Then, since y r is equal to bracket open 5 minus 16 over 1 plus 7 bracket closed into bracket minus 7 raised to power t plus 16 over 1 plus 7, equation 7.40 is equal to 3 into bracket minus 7 raised to power t plus 2. To check the answer, substitute t is equal to 0 and t is equal to 1 in equation 7.37. y0 is equal to 3 into bracket minus 7 raised to power 0 plus 2 is equal to 5. Since minus 7 raised to power 0 is equal to 1, y1 is equal to 3 into bracket minus 7 raised to power 1 plus 2 is equal to minus 19. Substituting y1 is equal to minus 19 for yt and y0 is equal to 5. For yt minus 1 in the original equation, minus 19 is equal to minus 7 into bracket 5 plus 16 is equal to minus 35 plus 16. The dynamic stability conditions. In general form, equation 7.38 can be expressed as yt is equal to ab raised to power t plus c. In equation 7.40, a is equal to y0 minus a over 1 minus b and c is equal to a over 1 minus b. ab raised to power t in equation 54 is called the complementary function and c is the particular solution. The intertemporal equilibrium level of y is expressed by the particular solution, while the complementary function represents the deviations from that equilibrium. Equation 7.40 will be dynamically stable only if the complementary function a b raised to power t approaches 0 as t approaches infinity. All this will depend on the base b. Assuming a is equal to 1 and c is equal to 0, for the moment, the exponential expression b raised to power t will generate 7 different time parts depending on the value of b. Example, time part of b raised to power t. From these diagrams, if absolute value of b is greater than 1, the time part will explode and move further and further away from equilibrium. If absolute value of b is less than 1, the time part will be damped and move toward equilibrium. If b is less than 0, the time part will oscillate between positive and negative values. If b is greater than 0, the time part will be non-oscillating. If a is not equal to 1, the value of the multiplicative constant will scale up or down the magnitude of b raised to power t, but will not change the basic pattern of movement. If a is equal to -1, a mirror image of the time part of b raised to power t with respect to the horizontal axis will be produced. If c is not equal to 0, the vertical intercept of the graph is affected and the graph shifts up or down accordingly. Exercise A. Solve the difference equation given below. B. Check your answer using t is equal to 0 and t is equal to 1. And C. Comment on the nature of the time part. Yt is equal to 6yt minus 1. 5yt plus 2yt minus 1 minus 140 is equal to 0. Y naught is equal to 30. Second order difference equations. The second order difference equations general solution composed of both complementary function and particular solution. Y function of t is equal to yc plus yp. Given the second order linear difference equation, yt plus b1 yt minus 1 plus b2 yt minus 2 is equal to a, equation 7.41, where b1, b2 and a are constant. The particular solution is yp is equal to a over 1 plus b1 plus b2. b1 plus b2 not equal to -1, equation 7.42. yp is equal to at over 2 plus b1. b1 plus b2 is equal to -1. b1 not equal to -2, equation 7.43. yp is equal to at squared over 2. b1 plus b2 is equal to -1. b1 is equal to -2, equation 7.44. And the complementary function is yc is equal to a1 r1 raised to power t plus a2 r2 raised to power t, equation 7.45, where a1 and a2 are arbitrary constants and the characteristic roots r1 and r2 are found using minus b1 plus or minus square root of b1 squared minus 4b2 over 2, given that b1 squared is not equal to 4b2. Example 1. Find the particular solution for the following equations. 1. Yt minus 10yt minus 1 plus 16yt minus 2 is equal to 14. 2. Yt minus 6yt minus 1 plus 5yt minus 2 is equal to 12. 3. Yt minus 2yt minus 1 plus yt minus 2 is equal to 8. For question 1, using the equation 7.42, yp is equal to 14 over 1 minus 10 plus 16 is equal to 2. Yp is equal to 12t over 2 minus 6 is equal to minus 3t. Yp is equal to 8t squared over 2 is equal to 4t squared. Example 2. The complementary function of equation 1 and 2 in example 1 using equation 33 and then substitute in equation 7.45 is r1 r2 is equal to 10 plus or minus square root of 100 minus 4 into bracket 16 bracket closed divided by 2 is equal to 10 plus or minus 6 over 2 is equal to 2 or 8. Thus, YC is equal to A1 into bracket 2 raised to power t plus A2 into bracket 8 raised to power t. For equation 2, R1, R2 is equal to 6 plus or minus square root of 36 minus 4 into bracket 5 divided by 2 is equal to 6 plus or minus 4 over 2 is equal to 1 or 5. Thus, YC is equal to A1 into bracket 1 raised to power t plus A2 into bracket 5 raised to power t is equal to A1 plus A2 into bracket 5 raised to power t. Characteristic roots. The characteristic equation have three different types of roots. They are 1. Distinct real roots, given that b1 squared is greater than 4b2. The square root in equation 33 will be a real number and R1 and R2 will be distinct real numbers. 2. Real roots that are repeated. If b1 squared is equal to 4b2, the square root of equation 33 will vanish and R1 and R2 will equal the same real number. The formula for YC in repeated real root will be YC is equal to A1 L raised to power RT plus A2 plus L raised to power RT, equation 7.46. YC is equal to A1 R raised to power T plus A2 plus R raised to power T, equation 7.47. 3. Complex roots. Equation 33 will contain the square root of a negative number if b1 squared is less than 4b2, and this is called imaginary number. In this case, R1 and R2 are complex numbers. A complex number contains a real part and an imaginary part. For example, 12 plus I, where I is equal to square root of minus 1. Example, the complementary function for equation 3 in example 1 above, where y prime prime function of t is equal to 16 is R1 R2 is equal to 0 plus or minus square root of 0 plus 4 into bracket 0 divided by 2 is equal to 0. Based on equation 60, R1 R2 is equal to 0, which is a case of repeated real roots. YC is equal to A1 L raised to power 0 plus A2 plus L raised to power 0 is equal to A1 plus A2 T. In question 3 of example, YT minus 2 YT minus 1 plus YT minus 2 is equal to 8. Solving for the complementary function from equation 33, R1 R2 is equal to 2 plus or minus square root of 4 minus 4 into bracket 1 divided by 2 is equal to 2 plus or minus 0 over 2 is equal to 1. However, based on equation 61, since R1 is equal to R2 is equal to 1, YC is equal to A1 into bracket 1 raised to power T plus A2 T into bracket 1 raised to power T is equal to A1 plus A2 T. This is the end of studies section 7. Thanks for listening.